Hello students, and welcome to section 6-5, Transformations of Exponential Functions. There is a model and discuss scenario that I'd like you to look at on your own. Typically these model and discuss scenarios, as we've seen in the past, will help kind of frame our understanding after the lesson specifically has been laid out with plenty of examples. I do want you to take a look at that and actually do so after we do these examples. And we will talk more about how these apply in context later, and I think in the live lessons, but also the homework discussion time and office hours and/or in the live lesson, you'll be able to get these questions even more specifically addressed. So example 1, vertical translations of graphs of exponential functions. How does the value of k affect the graph of f of x equals 2 to the x plus k? So this is clearly, I would argue, an exponential function. We're talking about a vertical translation though, particularly in the graph. So we're going to compare the graphs of g of x, which is 2 to the x plus 3, to this j of x function, 2 to the x minus 3. And we're going to do that with respect to what we call the parent function of f of x equals 2 to the x. Now, there is quite a bit to take a look at just from the tables alone, and then of course the graphs as well kind of speak to what will entail your understanding and application really. So the x f of x right here, this little table, you could argue if you just looked at that alone, speaks to, as you can see, 5 x values and 5 respective y values. This right here is a representation of what we call, again, the parent function. Okay, so if you plug in -2, 2 to the negative second, you take the reciprocal and write it as 1 over 2 to the positive second, which of course ends up being 1 over 4, or 1/4. Now I'm going to highlight the part of the graph that you see here with the black curve, wherein this point right here, -2, has a y value of 1/4. Similarly, -1, plugging it in, 2 to the negative first, take the reciprocal, you get 1 over 2, because 1 over 2 to the first is 1/2. And that speaks to this ordered pair right here. Okay, that's -1 comma 1/2, and so on and so forth. Plug in 0, 2 to the 0, that's 1. Plug in 1, 2 to the first is 2, and plug in 2, 2 to the second is 4. So those 1, 2, 3 remaining points on this black curve take shape, or allow the graph really to take shape. There is also a horizontal asymptote, if you recall, kind of limiting this graph as it goes off to negative infinity. Your y values technically never touch nor cross the horizontal asymptote or line y equals 0. The g of x function, using these exact same x values, if you plug in -2, just like we did essentially here, you could do it here as well, but as a quick reference point, just taking this, adding 3, because that's really what's happening, you're adding 3 to 1/4, so add 3 and you get 3 1/4. 1/2, again, that's the result of 2 to the negative first. There it is again on the g function. But adding 3 simply to 1/2 yields 3 1/2. Similarly, 1 plus 3 is 4, 2 plus 3 is 5, 4 plus 3 is 7. Okay, so that blue function has those respective ordered pairs. The graph of that exponential function, you can also note, has a horizontal asymptote up 3. And you can already see the notation here for translation as they describe 3 units up. So from the black to the blue curve, that's exactly what you're doing. Every point is moved up 3, up 3, up 3, and so on and so forth. The red function is going to be deciphered based on the subtraction of 3. Like we added 3 though, now we're subtracting 3 to these respective y's. So 1/4 minus 3, that's negative 2 3/4. 1/2 minus 3, that's negative 2 1/2. 1 minus 3 is -2. 2 minus 3 is -1, and 4 minus 3 is 1. So the red function that we see take shape is again dictated by the fact that you're shifting these points in black down 3 down 3, down 3. So the graph does nicely speak for itself, and as it describes off to the side and down below, there is a translation 3 units down. So the graph of f of x equals 2 to the x plus k is a vertical translation of the graph of f of x equals 2 to the x. If k is positive, the graph is moved up. If k is negative, the graph is moved down. And we see the difference between, again, the blue and the red functions, again, based upon the black parent function to start with. Let's move on. Example 2. So horizontal translations of graphs of exponential functions. It says compare the graph of g of x, which is equal to 2 to the x minus h, with the graph again of the parent function f of x equals 2 to the x when h is greater than 0. What effect does h have on the graph of g? So again, we should already have an idea what f of x equals 2 to the x looks like. We're going to choose an h value, particularly 5, and we're going to compare the graph of g of x equals 2 to the x minus 5 to the graph of f of x equals 2 to the x. The graph is already done for you, so we'll go ahead and take a look. Here's your black function, 2 to the x, and then here's the equation g of x equals 2 to the x minus 5. So here's the black curve. Here's the next curve where I guess maybe if we interpret that as maybe a different, I can use it, excuse me, on your calculator as a different color, because some calculators can do that. It's not visible as such, but you can, I hope, interpret based on kind of the move here. You're moving every point 5 units to the right, 5 units to the right, 5 units to the right. So this new curve here is just that type of transformation, okay? Or translation more specifically. So let's take a look. When h is greater than 0, the graph is translated h units to the right. The graph of g of x is a translation of f of x to the right by 5, or 5 units. For part B, compare the graph of j of x, which is equal to 2 to the x minus h, with the graph of f of x again equals 2 to the x. When h is less than 0, what effect does h have on the graph of f? So let h equal negative 3. So notice the function j of x is 2 raised to the x plus 3. On the prior example, it was minus 5, x minus h, and when you had 5 as a value, it ended up shifting to the right. In this case, you have negative 3 as your value, and look at the exponent highlighted as such, so x minus a negative 3 or plus 3. Let's compare. And here we go. So we can see, I would argue pretty nicely, that the, again, black function here, actually, technically the black function here, is the one that's represented as f of x equals 2 to the x. Well, this function, yes, it's still black, but again, certain calculators can actually differentiate with different colors, certain calculators. So this right here, let's call it the red function. That's a function, as you see, with the exponent as x plus 3, 3 left, 3 left, 3 left. So every point on this original 2 to the x parent function shifts 3 units to the left to get this new function graph. And that's described just below here. When h is less than 0, the graph is translated h units to the left. The graph of j of x is a translation of f of x to the left by 3. Okay. Example 3. Compare two different transformations of f of x equals 2 to the x. How can you compare the properties of g, given in the table, to the properties of j, given in the graph? Both functions are translations. Okay, so as we can see here, we're going to go ahead and take a look at their description of things, both in the table, but also graphically. The f of x table, it highlights these 5 ordered pairs, and you do see that on the graph with f in blue. While the g function, although you don't see it obviously on the graph, they give you some nice y values to assess. So negative 2 yields 2.25, negative 1, 2.5, and so on. So again, how do we compare the properties of g? Given in the table, to the properties of j given in the graph. J, as you can see, appears to be another exponential function, but clearly it looks to be a shift in some way, shape, or form down. There's other transformations we have yet to take a look at. But in combining g and j, those two, let's just call them points of data. We literally have points without seeing them on the graph for g, and we see technically on the j function curve actual points to identify with. So how do we decide what f and j are going to allow us to do with g? Step 1 is to compare g to f. The y-intercept of the graph of f is 1. The y-intercept of the graph of g is 3. Okay. Remember, we don't see the graph of g yet. The y values for g are 2 units greater than the corresponding y values for f. So 0.25 plus 2, 0.5 plus 2, 1 plus 2, 2 plus 2, and 4 plus 2. The asymptote of f is y equals 0. So the asymptote of g is 2 units greater, y equals 2. And we can argue that pretty confidently, like we saw in the prior example or two up above. One of the examples we saw where if you take the function and you add a number to it to get the other function's y values, it is it's a shift, it's a vertical shift technically up whatever that number happens to be. In this case, it's a shift up 2 units. So y equals 2 is the horizontal asymptote for the g function. Since the asymptote of g is y equals 2, the range of g would be simply y greater than 2 as compared to the range of f, which is y is greater than 0. So the graph of f nicely kind of speaks to the fact that there is a quote-unquote horizontal line or asymptote line that you can't see, of course, but it's limiting how these function values progress as x approaches negative infinity. Okay, as we continue, step 2, compare j to f. Now here is a really nice explanation as far as how the two compare. And you can kind of see, certainly the asymptote, as we already discussed, of f is y equals 0. The asymptote of j is y equals negative 1. And you can see that based upon how the graph kind of takes shape and progresses. This horizontal asymptote is negative 1 because as x approaches negative infinity, y approaches negative 1, never gets there. But that's the idea again with that particular function. The asymptote of j is 1 unit less than the asymptote of f. So quite literally it looks to be as if we're shifting it down a unit. Since the asymptote of j is y equals negative 1, the range of j is y greater than negative 1. So all the y values are above that particular horizontal asymptote as compared to the range of f, which was y greater than 0. Step 3, compare g to j. So in step 1 we compare g to f, step 2 j to f. Now how about g to j? The graph of g is the graph of f translated 2 units up, while the graph of j is the graph of f translated 1 unit down. So the graph of g is the graph of j translated 3 units up. Thus, the asymptote of g, if we were to graph g, is 3 units greater than the asymptote of j, and the y values of g are 3 units greater than the y values of j. I do recommend that you guys take a look and see if you can graph based on this explanation. See if you can graph the function g in comparison to, obviously, the other two. I believe that this is a good point of reference for us to get a good understanding as to how all exponential functions take shape and the translations and transformations that dictate them based on the parent function.